Please subscribe to support the channel. What does it mean for something to be infinite? In everyday language, infinite simply means without end. Something so vast, so unbounded, that no matter how far you go, there's always more. But in mathematics, infinity isn't just a really big number. It's an idea, a symbol that stands for endlessness itself, impassable to reach or measure. And when physicists and cosmologists talk about the universe being infinite, they're stepping far beyond mere abstraction. Does infinity, in the context of reality, have a physical presence? Is it a statement about what the universe actually is, or just a way for our equations to avoid dealing with inconvenient limits? To call the universe infinite is to say the cosmos has no edge, no boundary, no final frontier. If you were to travel in a straight line forever, you'd never hit a wall or wrap back around. But is this even possible in a universe governed by the laws of physics, quantum mechanics, and the fabric of space-time? In cosmology, when we use infinity, we're not just talking about a large number of stars or galaxies. We're talking about a structure that never ends in any direction on the largest scales imaginable. But here's the catch. Infinity in mathematics is clean and absolute. But in physical reality, it's slippery, dangerous, and maybe even nonsensical. Mathematicians are comfortable dealing with infinite sets and never-ending processes. But when we try to apply infinity to the real universe, the consequences can be staggering. If the universe is infinite, it contains an infinite number of galaxies, stars, and even copies of you. Everything that can happen does happen, somewhere, an infinite number of times. Is this physically meaningful or just a nightmare unleashed by equations unbound? When we talk about the shape of the universe, infinity takes on new implications. Is the universe infinite in volume, stretching endlessly? Or could it be finite but still have no edge, like the surface of a sphere? The question is not just about size, but about geometry and topology, the very shape of reality itself. And if the universe truly is infinite, what does that say about its structure, its curvature, its destiny? Physicists use the language of infinity with care, knowing it's a double-edged sword. An infinite universe might be easier to describe with certain equations, but it raises impossible questions about causality, duplication, and paradox. Are we simply using infinity as a placeholder for so big we can't measure it? Or is it an unavoidable conclusion of our current understanding? Some models, such as the flat universe suggested by measurements of the cosmic microwave background, point toward an infinite cosmos. But we can never observe infinity directly. We're always trapped inside our cosmic horizon, looking out at a patch of universe, trying to guess what lies beyond. So when we ask if the universe is infinite, we're not just toying with math. We're probing the limits of what existence itself can be. Infinity is not just large, it's total, absolute, and in many ways, terrifying. If the universe is infinite, every rule we think we know about beginnings, middles, and ends goes out the window. The very concept of everything changes. And the implications, physical, not just philosophical, are as vast as space itself. If infinity is such a perplexing concept, it gets even stranger when we bring in the idea of shape. You might think something infinite can't possibly have a shape. After all, if it never ends, what would its geometry even mean? But physics doesn't let us off that easily. In fact, the universe's shape is one of the most crucial questions in cosmology, and it's anything but a simple matter of edges or ends. To understand this, imagine what it means for space to have a shape. Not a shape in the way a rock or a planet has a shape, with a surface you can touch, but a shape defined by the way distances and paths work inside it. Here's where geometry, specifically non-Euclidean geometry, steps in. The universe could be flat, open, or closed. Each possibility means something drastically different for the fate of everything. In a flat universe, space extends forever in every direction. Parallel lines never meet, and the rules of Euclidean geometry hold. But flat doesn't mean featureless. It means the overall curvature is zero. If you travel in a straight line, you never return to your starting point. In this case, the universe could be infinite, with no edges, but no way to loop around. But what if space is curved? Consider a two-dimensional analogy, the surface of a sphere. If you walk in a straight line on a sphere, eventually you end up where you began. No edges, no boundaries, but also not infinite. The sphere's surface is finite, but unbounded. There's no edge to fall off, but also a limit to the total area. The universe in 3 dimensions could be like this, a hypersphere. You could travel in a straight line forever and eventually end up back at your origin without ever hitting a boundary. But now, take it a step further. Imagine a torus or the shape of a donut. In this scenario, space is still finite and unbounded, but its global properties are radically different. There's no edge, but the topology allows for more complex connections. Looping around one direction brings you back, but in another, maybe not. The rules for how you traverse the cosmos change depending on the topology. These are not just theoretical curiosities, they're legitimate possibilities for the shape of our universe, explored through the lens of Einstein's general relativity. But here's the chilling twist. Our universe could be both finite and edgeless, or infinite and edgeless. The observations, how light travels, how cosmic microwave background stretches, don't immediately tell us which is true. A finite, unbounded universe is possible. You could, in principle, circumnavigate it and return to where you started, like an ant crawling across a balloon. No boundaries, no walls, but also not endless. So when we ask if the universe can have a shape without boundaries, the answer is a resounding yes, and the options are stranger than you might imagine. It's possible for space to be finite in volume, yet have no edges, no ultimate limit, no place where it stops. The universe could be closed in on itself in higher dimensions, looping eternally. Or it could be infinite, stretching on and on without edges or returns. Geometry and topology give us the tools to describe these cosmic possibilities. And as far as observations go, both remain on the table, lurking in the math and the mysteries of cosmic structure. The very shape of the universe could mean everything we know is just a small piece of a much more mind-bending reality. One where boundaries are illusions and infinity wears the mask of finite forms.
So if the universe can be both finite and edgeless, or even infinite and edgeless, what does it actually mean for us as travelers in space? What happens if you pick a direction and never stop moving? This is where the difference between our intuition and the harsh reality of cosmic geometry comes into sharp focus, and where things get truly thrilling. In a finite but unbounded universe, the rules of travel become as strange as the surface you move on. Picture yourself as that hypothetical ant on the surface of a globe. There's no edge to the globe, you'll never find a cliff to fall off of, but keep moving in a straight line and eventually you loop back to your starting point. You'd cross what feels like unending terrain only to find that you've arrived back where you began without ever encountering a wall or border. This isn't fantasy. This is exactly what physics tells us is possible with certain cosmic geometries. In a closed universe, like a hypersphere in 3 dimensions, travel long enough and far enough and the universe delivers you back to where you started. No edge required. No matter how far you go, you can never leave. But what if the universe is infinite, unending in all directions? Does that guarantee there's no edge at all? Here's where things become unsettling. If the universe is infinite, you'd expect there could be no edge, because where would you put one? An edge implies something exists beyond, something to cross into or out of. In an infinite universe, the very idea of an edge starts to lose meaning. But the question remains, is there any scenario where infinity and edge coexist? Physically, the concept of an edge to an infinite universe is almost impossible to sustain. In mathematics, infinity stretches without end. In the physical universe, we don't see any evidence of a boundary, a cosmic wall, a last galaxy, or a final frontier where reality abruptly stops. If you kept traveling, you would keep encountering more and more of the same. More galaxies, more voids, more cosmic structures forever. The laws of physics don't predict an edge for space itself, at least not in any theory that matches our observations. But here's the twist. In some models, especially those dealing with higher dimensions or exotic topologies, you can imagine boundaries or transitions that don't look like edges in the conventional sense. These could be regions where the properties of space change, where physics itself might shift, or the rules that govern our universe might end and something totally unknown takes over. But even these boundaries aren't edges, like the edge of a table. They're more like transitions, domain walls, or places where space-time fold into something new. No step off a cosmic precipice, no set and stop, just a change in the rules of existence. And yet, we have to ask, are we missing something? Could an edge exist hidden from our perception by the limits of observation or the laws of physics? Could there be places in the universe so strange that what we think of as an edgeless cosmos is really just a local illusion? This isn't science fiction. In some speculative scenarios, an edge could take the form of a phase transition in the vacuum of space, a break in the laws of physics, or a contact point with another universe entirely. For now, all evidence points to an edgeless universe, at least within the limits of our observation. Whether space is finite and wraps around itself, or infinite and unending, the cosmos appears to be constructed with no physical edge, no wall, no fence, no curtain marking the end of existence. The idea of an edgeless universe is not only possible, it's entirely consistent with what we see and measure. But what lies beyond our comprehension may still hide surprises no one has yet imagined. If we keep digging into the structure of the universe, the notion of an edge becomes not just strange, but paradoxical, almost self-destructing under the weight of what it means. Let's say, for the sake of argument, the universe actually does have an edge. What happens at that limit? Is it a wall, a void, a zone of destruction, or a barrier you can never cross? The truth is, the very idea of an edge instantly raises a much deeper, almost explosive question. If there is an edge to the universe, what's on the other side? And is there any meaningful sense in which an outside could even exist? Here's where things get technical and where physics throws a wrench into our basic instincts. The universe, by definition, is everything. All of space, time, energy, matter, and the laws that bind them. So if you say there's an edge, you're instantly forced to define what exists beyond. If there's a beyond, it would have to be something that isn't part of our universe. Maybe it's a region where the fabric of space-time simply doesn't exist. No distances, no time, no energy, not even nothing. And if that's the case, can you even say it exists at all? Or are we dealing with a concept that makes no sense in the language of physics? In classical terms, an edge always implies two things: the thing itself and whatever lies outside it. The edge of a table is the boundary between wood and air. The edge of a continent is where land meets sea. But with the universe, the situation is much more extreme. Space itself is part of the universe. There's no air outside, no ether, no bigger space holding our cosmos. General relativity, the fundamental theory of space-time, describes the universe as a manifold, a seamless, self-contained fabric with no need for an outside. In this model, an edge to the universe isn't the thing you can reach or touch. There's no place to go, no direction to point, no observer who could ever step outside and look in. Even the void beyond a cosmic edge wouldn't be a place. It wouldn't be anything. Some speculative theories play with the idea of an edge, but details get brutal. Could the universe have a boundary? A physical surface where all known laws break down? Maybe yes, but nothing in the equations of general relativity suggests such a thing. A hard edge would be a singularity, a place where space-time curves to infinity, the laws of physics break, and all bets are off. This isn't just a border, it's the end of physics itself. If you could even reach such a boundary, nothing could cross it. Signals couldn't escape, objects couldn't pass. The universe would be like a cosmic black box. Inside you exist, outside there's not even the concept of existence.
But what about the quantum realm? Could quantum mechanics allow for an edge in a more subtle, probabilistic way? Quantum field theory treats space-time as a stage on which fields play out. And those fields don't just cut off at an arbitrary wall. If you tried to impose an edge, you'd break the symmetries that the universe appears to obey. The results would be catastrophic. Vacuum instability, unpredictable quantum effects, maybe even tearing the universe apart. In the real world, there's no evidence, none at all, of such an edge or abrupt limit. Cosmology sometimes hints at edges, but only as limits of our perception. The observable universe has a boundary, a cosmic horizon beyond which light hasn't had time to reach us since the Big Bang. But that's not a real edge, it's just a limit to what we can see. The universe may go on forever beyond this horizon, or it might loop back on itself. We have no direct way to know. If there were an edge, it would be fundamentally different from anything we've ever encountered. A breakdown not just of material or space, but of the very rules that make reality possible. Here's the kicker. If the universe did have an edge, it would demand an explanation. What causes it? What's special about that particular place? Why is the universe finite in one direction, but not another? In physics, such asymmetries usually signal missing information or flawed assumptions. The more we study the cosmos, the less likely an edge seems. The equations of general relativity, the observed uniformity of the cosmic microwave background, and the sheer consistency of physics all point toward a universe without borders. But there's an even more unsettling implication. If an edge does exist, it could mean that the universe is part of something larger, a metacosmos, a superuniverse, a multiversal landscape with regions beyond our own. In this scenario, our universe might be a bubble in a vast sea of bubbles, each with its own laws, boundaries, and edges. But even then, the question returns. What's outside that? It's turtles all the way down, or worse, an endless regression that physics cannot answer. At the cutting edge of theory, some physicists explore boundaries in higher dimensions, like branes in string theory, or the walls between pocket universes in eternal inflation. In these models, our universe's edge is really a transition, a change in the laws or the number of dimensions, not a brick wall. But even these ideas are speculative, with no experimental evidence to back them up. So, does an edge mean there's an outside? According to everything we know in physics, not in any way that makes physical sense. The universe is, by definition, all there is. If there's an edge, it's not an edge in the way we imagine. It's either a mathematical artifact or a signal that our models are incomplete. The idea of an outside may be an illusion, a product of our brains evolved to deal with finite objects and bounded spaces, not the unbounded, edgeless expanse of reality as revealed by science. What we find again and again is that the universe plays by rules far more alien and thrilling than anything in ordinary experience. Edges, boundaries, outsides, these are categories that break down in the face of cosmic reality. The notion of an edge may be flawed not just because we lack evidence, but because it misunderstands what the universe fundamentally is, a self-contained totality with no place else to go. If the universe is infinite, and has been infinite since the beginning, what does it actually mean when cosmologists say it's expanding? Here, the conversation enters territory that's almost impossible to grasp with ordinary logic, because the expansion of space doesn't just happen at the edges of the universe or by adding more galaxies to the outside. In an infinite universe, the expansion is a property that plays out everywhere, all at once, even as the total size remains, by definition, without limit. Let's start with the basics. In the standard model of cosmology, the universe has been expanding since the Big Bang. Galaxies aren't flying apart through empty space. Space itself is stretching, carrying galaxies away from one another. This isn't just a metaphor. Measurements of the light from distant galaxies show a redshift. The wavelengths of light are literally stretched as space expands, telling us the universe was smaller, denser, and hotter in the past. But if space is already infinite, what does expansion mean? Does infinity just get bigger? The answer is as counterintuitive as it is thrilling. Mathematically, the size of an infinite set doesn't increase in the way finite things do. Infinity plus infinity is still infinity. So when cosmologists talk about an infinite universe expanding, they don't mean it's getting bigger in a way that adds more space beyond some boundary. Instead, the expansion refers to the scale of space, the distances between objects, growing over time. Imagine an endless grid stretching forever in all directions. If you double the distance between every point in the grid is still infinite, but the spacing has changed. That's what happens in an infinite expanding universe. The scale factor, the mathematical quantity that tells you how big distances are relative to the past, increases. All points move farther apart, but there's still no edge, and the total amount of space remains infinite. There's no center, no boundary, and no place that isn't expanding. This isn't just a theoretical curiosity. The current evidence from the cosmic microwave background, the distribution of galaxies, and the dynamics of large-scale structure all point toward a universe that, on the largest scales, is flat and potentially infinite. And it's expanding, not by adding more stuff to the outside, but by stretching the very fabric everywhere at once. So, how do physicists make sense of this? They use the concept of co-moving coordinates, a mathematical trick that lets us track the positions of galaxies as the universe expands. In co-moving coordinates, the points themselves don't move, but the distances between them grow over time as the scale factor increases. The universe's geometry, encoded in the metric of general relativity, tells us how to calculate these changes, and the math works even if the underlying space is infinite.
But what about the energy, the matter, the stuff of the universe? As the universe expands, the average density of matter decreases. In a finite universe, you could calculate the total mass and energy. In an infinite universe, these totals are always infinite, but the density, how much mass or energy per unit volume, gets smaller as space expands. Photons lose energy as their wavelengths stretch, a direct result of the universe's growth. And then there's the biggest mind-bender, acceleration. Observations show the universe isn't just expanding, it's accelerating. Galaxies are being driven apart faster and faster by dark energy, a mysterious form of energy woven into the very vacuum of space. In an infinite universe, this means that more and more regions are rushing beyond each other's reach as space expands so quickly that light from one part will never reach another. The observable universe shrinks in terms of what we'll ever be able to see or interact with, even as the total universe remains infinite. How do we measure or comprehend this growth? Cosmologists rely on mathematical models, precision observations, and the relentless logic of general relativity. We can't see the whole infinite universe, but we can measure the expansion rate, the Hubble constant, the redshift of galaxies, and the stretching of cosmic microwave background photons. These let us reconstruct the history of expansion and infer its future. The numbers are huge and the implications are staggering, but the logic is airtight. An infinite universe can expand not by growing larger in any conventional sense, but by stretching distances everywhere, forever. And this isn't just an abstraction. If the universe is infinite and expanding, it means there are regions so far away, moving away so rapidly, that light from them will never reach us. Not in a trillion years, not ever. The cosmos becomes an infinite mosaic of disconnected worlds, each cut off by the relentless growth of space itself. So, when we talk about the expansion of an infinite universe, we're dealing with a reality where growth means the stretching of everything, everywhere at once.
Infinity doesn't get bigger, it gets more separated, more isolated, more strange. The mathematics holds, the observations confirm it, and the result is a universe where the unimaginable is made real. Infinite space, forever expanding, with no edge, no outside, and no end. When people imagine the universe expanding, there's an instinct to picture something like a balloon inflating, a growing sphere with a clear boundary, an edge that moves outward into emptiness. But this mental image, while tempting, is fundamentally misleading. In the actual physics of our universe, the expansion of space isn't about pushing into some pre-existing void or making more room at the frontier. Instead, it's a stretching of the fabric of reality itself, and the question of whether there's an edge becomes both more precise and far more mysterious. Let's start by demolishing the balloon analogy. In that scenario, the edge is the balloon's rubber surface, and outside is the surrounding air. But with the universe, there's no outside. The universe isn't expanding into anything. Space itself is what's getting bigger, everywhere, all at once. There's no shell, no wall, no region that marks where the universe ends and something else begins. The expansion happens internally, to distances, not into external territory. This is a direct consequence of general relativity, which describes space and time as a four-dimensional fabric, not something floating in a bigger space. But if there's no edge, how do we make sense of the observable universe, that vast region we can actually see? Here's where the concept of the cosmic horizon comes in. The observable universe is bounded, but not by a physical edge. It's limited by time and the speed of light. The Big Bang happened about 13.8 billion years ago, and light can only travel so fast. So the most distant galaxies we can detect are those whose light has just barely had time to reach us since the universe began. This forms a cosmic light horizon, a sphere centered on us, marking the limit of our vision. But, and this is critical, beyond that horizon, the universe almost certainly continues. There's nothing special or unique about our location. So, if you were standing on a planet in a distant galaxy, your observable universe would have its own horizon, centered on you, overlapping but not identical to ours. Every observer, no matter where they are in the cosmos, has their own personal horizon, a limit not of existence, but of observation. Is this horizon a true edge? Absolutely not. It's not a barrier you could ever reach, no matter how fast you travel. In fact, as you move forward in time, light from distant regions has time to reach you, and your observable universe grows. But the total universe, whether infinite or simply much larger than what we can see, doesn't end at the horizon. The horizon is a moving limit, not a frontier. Now here's where it gets really wild. Because the universe is expanding, and because distant galaxies are moving away from us faster than the speed of light, thanks to the expansion of space itself, there are regions that we will never see, even given infinite time. Their light can never catch up to us because the space between us and them is stretching faster than light can traverse it. This sets another, more absolute kind of cosmic boundary, the event horizon. Galaxies that are receding faster than light due to cosmic expansion are forever cut off from us, not because of a physical wall, but because of the relentless, unstoppable growth of space itself. But even these horizons are not true edges. There is no physical marker, no wall in the void, no last galaxy sitting next to nothingness. The edge is always an illusion, a trick of our perspective and the finite speed of light. The universe could be infinite in extent, or it could be so vast and closed in on itself that its edges wrap around in ways we can't directly perceive.
Could there be any sense in which an edge exists physically?
According to every testable model in modern cosmology, no. All observations and the mathematical structure of general relativity support the idea that space is either infinite or finite, but without a boundary. If you could somehow travel far beyond our horizon, you wouldn't find an edge. You'd just discover more space, more galaxies, more of the same cosmic tapestry. The structure of space itself would continue, unbroken. In practical terms, then, the expansion of the universe gives rise to boundaries in information, not in space. The observable universe is a bubble defined by what we can see, not by where the universe stops. The true cosmos, the whole of reality, is either boundless, looping in on itself without edges, or simply infinite. There is no evidence for a hard frontier, no suggestion in the data of a discontinuity where existence ends. And yet, the consequences of expansion are dramatic. As the universe ages, more and more regions slip beyond our ability to ever contact or even observe them, lost forever behind the accelerating expansion of space. The cosmic horizon grows, but the event horizon, the ultimate limit set by cosmic acceleration, means that most of what exists will always remain beyond our reach. So, what happens at the edge of the expanding universe? The thrilling, almost unsettling answer is nothing at all, because there is no edge, only the ever-shifting boundaries of what's visible, knowable, and causally connected. The universe expands, the horizons move, but the edge, as a physical reality, simply does not exist. The geometry of the universe is far stranger than anything we experience in daily life. While our brains are wired to imagine three-dimensional space as a simple, endless box or a finite sphere, the possibilities that come out of higher mathematics and cosmology are far more exotic and infinitely more thrilling. What if the universe could be infinite in some directions, but finite in others? What if the shape of all reality is more like a cylinder, a torus, or even a twisted Mobius strip? Could the cosmos itself have dimensions that loop, wrap, or even cross themselves in ways that defy conventional logic? To make sense of this, let's turn to the language of topology, the study of spaces and surfaces, and how they can be connected, stretched, or looped. Imagine, for a moment, living in a two-dimensional universe, a flat sheet that extends forever in one direction, but is rolled into a cylinder in the other. In this universe, if you head east or west, you'll eventually return to your starting point, having looped around the cylinder's curved surface. But if you travel north or south, you could keep going forever, never looping back. Here, your world is finite in one dimension and infinite in another. There's no edge, just a global structure that links up in an unexpected way. Now take it further. Imagine the universe is like the surface of a torus, a donut shape. In two dimensions, both directions loop around. Travel far enough in any direction, and you'll return to where you began. This is a universe that's finite, without boundaries, but with a fundamentally different topology than a sphere or a plane. No edges, no ends, but also not infinite in area. In three dimensions, things get even more bizarre. The universe could be a three-torus, a space where every axis, length, width, height, loops back on itself, creating a finite but edgeless cosmos, impossible to picture but perfectly sound mathematically. But what about a Mobius strip, a surface with only one side and one edge? In principle, the universe could have a similarly twisted topology in higher dimensions. If you could travel far enough, you might find that your orientation flips. What was once left becomes right, or up becomes down. The universe would be a cosmic funhouse mirror, finite but without clear boundaries, and fundamentally non-orientable. Here's where higher dimensional geometry ramps up the strangeness. The mathematics of general relativity allows for space-time to be shaped in almost any way, so long as the local curvature matches the energy and mass inside it. Some models of the universe, known as compactified dimensions, suggest that extra spatial dimensions could be rolled up to tiny scales, invisible to us, but real nonetheless. In string theory, for example, The universe may have as many as 10 or 11 dimensions, with most of them compactified into loops or exotic shapes too small to detect. But could our familiar, large-scale universe be infinite in some directions and finite in others? Absolutely. Cosmologists call these multiply connected universes. In such a cosmos, space might repeat itself on a grand scale, a kind of cosmic hall of mirrors. Light from a distant galaxy could loop around the universe and millions or billions of years later return to us from the opposite direction. In principle, if the universe's topology is just right, we might even see multiple images of our own Milky Way, displaced by enormous cosmic distances. The quest to discover the true topology of the universe is ongoing. Physicists study the cosmic microwave background, looking for repeating patterns or matched circles, potential evidence that light has wrapped around the cosmos and returned to us. So far, no such patterns have been conclusively found, but the possibility remains open. The universe could be spatially infinite, or it could be finite, but without any edge. A vast, self-contained loop or web of connections so vast, we've never seen a single repeat. And even more thrilling, higher dimensional models suggest that edges could exist only in the context of extra dimensions we cannot perceive. Our three-dimensional universe might be a brain floating in a higher dimensional bulk, with boundaries in dimensions we never experience. These aren't walls you could touch or cross, but mathematical limits to the way space and time can behave. So could the universe be infinite in some dimensions but not others? Could it have boundaries in ways that make sense only in higher dimensional math? The answer, supported by both theory and observation, is a resounding yes. The cosmos may be vastly more complex than a simple infinite expanse or a closed sphere. It could be wrapped, twisted, and connected in ways that challenge all human intuition, and the search for evidence, subtle patterns in cosmic radiation, echoes of light from distant pasts, or clues buried in the fabric of space-time itself, continues, pushing the limits of observation and imagination. In the end, the very shape and connectivity of the universe might hide clues to its origin, its fate, and the deepest laws that govern everything. Geometry and topology aren't just mathematical curiosities. They're the key to understanding whether the universe is infinite, bounded, twisted, or something stranger still. Now let's veer into territory that's as unsettling as it is cutting edge. What if the universe itself is not a physical structure, but a digital simulation running on some unimaginably advanced computer? In this scenario, every particle, every law, every galaxy, even the flow of time is the result of computational processes coded by some form of intelligence or algorithm. If that's true, could the universe appear infinite to us while actually being governed by hard limits, by boundaries written in the underlying code? Could there be an edge that's not a physical wall, but a digital constraint, a maximum value, or a region where the simulation just runs out of data? First, let's be clear. The simulation hypothesis isn't just science fiction anymore. Leading thinkers in physics, philosophy, and computer science have debated the possibility, sparked by advances in virtual reality, quantum computing, and our ever deeper understanding of information theory. If our universe is a simulation, then what we perceive as continuous reality is, at the deepest level, discrete, chopped into tiny bits like pixels on a screen or bytes in a file. Space, time, energy, and even consciousness could be emergent properties, the output of a cosmic algorithm. So, could a simulated universe be infinite? From inside the simulation, yes. If the rules are programmed to generate new space, matter, and events on demand, the simulated universe could present itself as infinite to any observer within it. But from the outside, from the perspective of the computer or its creators, there are limits. There's only so much processing power, only so much memory, only so much data that can be stored or computed at any moment. The universe might appear infinite, but it could actually be running on finite resources, with clever code ensuring that observers never see the seams. Now, what about digital boundaries? Could there be coded edges, places where the simulation just stops? In theory, yes. The simulation might only generate detail where it's needed, just as a video game renders high-resolution textures only in the player's immediate vicinity, leaving distant areas vague or undefined. If no observer ever travels beyond a certain limit, why waste resources simulating what's not being watched? In such a world, the edge could be a hard cutoff, a void, or a strange region where the laws of physics break down, computation slows, or anomalies appear. Would we ever detect a glitch at this boundary? That's the million-dollar question. If the simulation is sophisticated enough, it could mask its boundaries, ensuring that anyone approaching the edge is subtly redirected or that the simulation extends itself seamlessly as needed. But if the coding is imperfect, or if there are constraints that can't be hidden, it's possible we might observe unexplainable phenomena. Sudden breakdowns in physical law, repeating structures, impossible patterns in the cosmic background, or even digital artifacts, glitches in the matrix. Physicists have already looked for clues. Some have examined the distribution of high-energy cosmic rays, searching for lattice patterns or anomalies that might suggest a grid underlying space. Others have proposed that if space and time are fundamentally digital, there might be a smallest possible unit, a pixel of space-time, the Planck lengths and Planck time, beyond which the simulation can't subdivide reality any further. The search is ongoing, and while no definitive evidence has been found, the absence of proof doesn't close the case. A well-designed simulation could simply hide its limits more cleverly than we can detect. This hypothesis forces us to rethink what an edge even means. It's not a place you can reach in a spaceship or a zone where you'd fall off into nothingness. It could be a limit on complexity, a region where physical constants change, or even a subtle shift in the laws that govern computation itself. Perhaps, if we ever detected such a boundary, it would be in the form of a fundamental limit to information density, a maximum speed of causality, or an abrupt change in quantum behavior. But here's the kicker. Even if our universe is a simulation, it's still our universe. The rules are still consistent, the physics still predictable, and the cosmos still overwhelmingly vast and complex. If there is an edge, digital, coded, or otherwise, it might always remain out of reach, protected by the very logic of the system itself. Or it could mean that the simulation is, in a very real sense, infinite for all practical purposes, even if it's ultimately running on finite machinery. So, does the simulation hypothesis suggest a new way to think about cosmic edges? Absolutely. It opens the door to boundaries that aren't spatial but computational, limits that are enforced not by the nature of space but by the rules of code. In a simulated universe, the edge is wherever the code says it is, or nowhere at all if the system is robust enough to hide its own architecture from its inhabitants. In the end, the possibility that our reality is simulated doesn't make the cosmos any less real, any less strange, or any less worthy of scientific exploration. It just adds another deeply unsettling layer to the question of boundaries, a reminder that what we perceive as infinite, continuous, and edgeless might ultimately be the artifact of lines of code, running somewhere beyond all possible observation. When we plunge into the realm of the very small, the idea of a cosmic edge faces a new kind of test. A test governed by quantum physics, where the smooth, predictable flow of space and time breaks down into something far more chaotic, granular, and probabilistic. Does quantum theory allow for a sharp, absolute boundary at the edge of the universe? Or does it dissolve all hope of a hard edge, replacing certainty with fundamental fuzziness? In quantum scale, everything, not even space and time, is ever perfectly sharp or well-defined. Positions blur, energies fluctuate, and the Heisenberg uncertainty principle guarantees that the more precisely you try to know one property, the more uncertain another becomes. Space and time themselves, once thought to be the stage on which particles perform, are increasingly seen as players in the drama, subject to the same rules of uncertainty and probability as matter and energy. First, let's consider what it would mean for a boundary, an edge, to exist at the quantum level. In classical physics, a boundary is absolute, but in quantum mechanics, the very act of defining a sharp edge is fraught with paradox. If you try to localize a particle perfectly, to pin it right at an edge, the uncertainty in its momentum becomes infinite, meaning it could be anywhere doing anything. The edge itself becomes undefined, smeared out by quantum fluctuations. Instead of a crisp line, you get a hazy region where probabilities rule. Quantum field theory, the best tested theory in all of science, extends this uncertainty to the very fabric of the vacuum. The fields that make up everything, electromagnetic, weak, strong, even gravity, are never truly at rest. they seethe with quantum fluctuations, particles popping in and out of existence, energies rising and falling. Try to impose a sharp boundary, a literal wall at the edge of the universe, and you immediately create wild effects. Virtual particles would pile up against the edge, vacuum energy would spike, and the boundary would become a region of intense, unpredictable behavior. In fact, physics predicts that sharp boundaries generate phenomena like the Casimir effect, where quantum fluctuations create measurable forces between closely spaced plates. On a cosmic scale, such effects would be catastrophic, possibly tearing any hard edge apart or creating new exotic phases of matter. But what about abrupt changes in the laws of physics? Could quantum uncertainty allow for a boundary where on one side the rules are one way and on the other they change entirely? Quantum theory does allow for domain walls, regions of space with different properties, like distinct phases in a material. In the early universe, during cosmic inflation, phase transitions could have created such walls, separating regions with different vacuum states or physical constants. But these domain walls are not hard edges, they are transitional zones, often with their own rich physics, where energy, particles, and fields interact in new ways. There's another layer, quantum gravity, the as-yet untamed theory that must unite Einstein's smooth spacetime with quantum fuzziness. Here, the very concept of a location in space may lose all meaning at the smallest scales. Some leading ideas, like loop quantum gravity and string theory, suggest that space-time itself is quantized, made of tiny, indivisible units. If so, there might be a fundamental limit to how sharp any boundary can be. At the Planck scale, roughly 10 to the negative 35 meters, all our intuitions about continuity and edges break down. Any edge at this scale would be hidden by quantum foam, an ocean of flickering geometry, where space and time come into being and vanish in a ceaseless churn. And yet, quantum theory is not completely lawless. In principle, it allows for abrupt transitions, changes in physical law across a domain wall, the birth of bubble universes in inflationary models, or even the formation of a cosmic event horizon at a black hole's boundary. But in every case, the transition zone is never truly sharp. There's always a region of quantum uncertainty, a liminal space where the old rules fade and the new ones take over, governed by probabilities and the relentless mathematics of wave functions. Could the quantum structure of reality ever reveal an edge to the universe? As of now, there's no evidence that such a hard boundary exists. Instead, quantum mechanics seems to demand the absence of true edges. Even the observable limits of our universe, the cosmic horizon, are smeared by quantum effects. The edge is always a region, not a line, a probability, not a certainty. What quantum physics does allow, however, is the possibility of unexpected boundaries. If the vacuum of space can exist in multiple states with transitions between them, then perhaps there are regions of the universe, unreachable to us, where the laws themselves are different. But those boundaries, if they exist, are always regions of transition, turbulence, and quantum chaos. In the end, the quantum world doesn't just resist the idea of a sharp edge, it replaces it with a realm of probabilities, fluctuations, and endless complexity. Every time we try to pin the universe down to find a final wall or a last frontier, quantum uncertainty steps in and shatters the illusion. The cosmos, on its most fundamental level, may simply be incapable of supporting a true edge. It is, instead, an endless field of possibilities, ruled not by walls or barriers, but by the deep, strange order of quantum law. If the universe were to have an edge, what would it truly mean? Would it be the end of everything? Or could it actually be a boundary with something even stranger, a neighboring universe with entirely different properties? This is the point where science begins to overlap with some of the wildest yet rigorously considered ideas in modern theoretical physics, the multiverse. In the multiverse scenario, our universe might not be all there is. Instead, it could be just one region, one bubble or domain among countless others, each potentially with its own physical laws, constants, dimensions, and histories. The concept of the multiverse isn't just idle speculation. It emerges naturally from several leading-edge theories, including cosmic inflation, string theory, and even quantum mechanics. If such a multiverse exists, then the edge of our universe might not be a hard stop, but a frontier, a transition zone between our cosmos and another, fundamentally different one. Consider the model of eternal inflation, a direct extension of the Big Bang. In this framework, the rapid inflationary expansion of space doesn't end everywhere at once. Instead, pockets of space stop inflating at different times, creating bubble universes separated by expanding inflating regions. Each bubble could become a universe with its own properties, and the space between them, the so-called inflating false vacuum, remains forever out of reach. If you could somehow reach the edge of our bubble, you wouldn't hit a wall, you'd hit the inflating boundary, possibly entering a region of space still tearing itself apart at exponential speed, or, with even more dramatic consequences, colliding with another universe and witnessing the breakdown of everything familiar. String theory, too, predicts the possibility of a multiverse. Its equations allow for an almost unimaginable number of stable configurations, each corresponding to a universe with different physical laws. These different vacua are like different valleys in a vast energy landscape. Tunneling from one vacuum to another could generate a new universe, each separated by domain walls. In this model, the edge of one universe is simply the start of another, with a potentially violent transition zone in between. But what then contains all these universes? What is the space of the multiverse? Here the questions turn radical. In eternal inflation, the inflating space itself, the false vacuum, is the medium in which bubble universes appear and evolve. In string theory, the landscape of possible universes isn't embedded in any higher dimensional space we can comprehend. Instead, each universe is self-contained, with its own space-time, causality, and perhaps even its own mathematics. There's no outside as we understand it. The multiverse is not a collection of universes floating in a higher dimensional box. It's a collection of entirely separate, possibly causally disconnected realities with transitions that may be more like phase changes in a cosmic superstructure than travel across a border. Quantum mechanics offers yet another path to the multiverse, through the many worlds interpretation. Here, every quantum event with multiple possible outcomes creates new branches of reality, splitting the universe into an ever-expanding tree of parallel histories. In this scenario, there's no physical edge, just an endless proliferation of alternate universes, each as real as ours, but forever separated by the laws of quantum decoherence. If these universes have boundaries, they're boundaries in information, not in space.
Can we ever probe or detect the edge of our universe if it is a transition to another? In principle, some theorists have speculated about observational signatures. If two bubble universes collided in the distant past, the impact could leave imprints in the cosmic microwave background, circular scars, or unusual patterns. To date, no such signals have been confirmed, but the search continues. Others have suggested that if the fundamental constants of nature vary across different regions, we might see strange shifts at the furthest observable distances. Again, the evidence is not yet there, but it's not ruled out. Perhaps the most unsettling possibility is that the space containing all these universes, the so-called metaspace or superspace, has no physical existence at all. It may be a purely mathematical structure, a set of relationships and possibilities with no need for spatial embedding. In this view, each universe is self-contained, with its own definition of space, time, and existence, and there is no overarching arena that contains them all. If there is a multiverse, and if our universe does have an edge, that edge is not a wall at the end of space. It's a transition, possibly unreachably distant, possibly utterly inaccessible, where the rules of physics could break down, new laws could take over, and everything familiar could vanish in an instant. It's a concept that stretches the limits of what science can test, but one that emerges naturally from the mathematics of our best theories. And if these ideas are correct, then our universe is just one of countless possibilities, each isolated, but each part of a larger, richer, and far more terrifying reality. The edge of our universe might not be the end,
but just the start of a cosmic expanse whose full extent we may never know. We talk about the observable universe as if it's synonymous with the universe itself, but in reality, it's just a fraction, a cosmic postage stamp of what might be out there. The observable universe is defined by the distance that light has been able to travel since the Big Bang, around 13.8 billion years ago. Thanks to the expansion of space, the actual radius is about 46 billion light-years in every direction, giving us a visible sphere roughly 93 billion light-years across. That's a mind-bending distance, filled with hundreds of billions of galaxies, trillions of stars, and even more planets. But the crucial detail is this: the observable universe is not the universe. It's simply the paths of the cosmos that we can see, limited not by any physical edge, but by the speed of light and the age of space itself. Imagine you're standing on a vast plain that stretches forever in every direction, shrouded in dense fog. You can see a certain distance, but beyond that, everything is hidden. The edge of your vision isn't the end of the plain, it's just the limit of what's visible. The universe works exactly the same way. The cosmic edge we see, the boundary of our observable universe, is simply a horizon, dictated by how far light has traveled to reach us. Beyond that, there's no evidence of a wall, a boundary, or a final frontier. The cosmos could continue forever, with galaxies and clusters beyond clusters, an endless succession of cosmic structures we'll never see. This distinction isn't just a technicality, it's foundational to understanding modern cosmology. The universe may well be infinite, or at least so vast that the observable region is a microscopic speck in the grand scheme. Even if the universe is finite but wraps around itself, the region we can access is still limited by the finite speed of light and the finite time since the Big Bang. There could be regions of space so far away that their light will never reach us, not in a trillion years, not ever, because the expansion of the universe is carrying them away faster than light itself can travel. All the evidence we have, from the smoothness of the cosmic microwave background to the distribution of galaxies to the laws of physics themselves, suggests that the universe continues well beyond what we can see. The same patterns, the same rules, the same physical constants appear to hold in every direction, with no sign of a boundary or edge within reach. Yet, the observable universe is all we have direct access to. Everything beyond it is, for now, forever out of contact. Could the edge we perceive, the edge of our observable universe, just be the limit of our measurements, not of existence itself? Absolutely. This edge is not a physical barrier, it's a horizon set by time and causality. Light from beyond that horizon simply hasn't had enough time to get here. And because the universe is expanding, some regions are receding so quickly that even light emitted now will never catch up. Our observable universe is always finite, always limited, and always shrinking as a fraction of the whole as time goes on. This isn't just theoretical, there are real observable consequences. Some light we detect today, like the cosmic microwave background, was emitted when the universe was just 380,000 years old, and has been stretched across billions of light years by the expansion of space. As time passes, distant galaxies slip over our cosmic horizon, their light stretched and dimmed until it fades away, lost to us forever. The farther we look, the older and more primitive the universe appears. But there's no sign that we're nearing a border or that space itself is running out. The most extreme implication is that for all practical purposes, the universe could be infinite, and our observable region is just a local neighborhood. There may be entire regions of the cosmos where galaxies have formed and died, where stars have burned out, where the laws of physics could be slightly different. In some models, every possible event not forbidden by physical law occurs somewhere an infinite number of times in regions forever beyond each other's reach. And yet, we are trapped. The edge we see is an observational horizon, not a physical one. All of our science, all of our data, every experiment and measurement is confined to this bubble of light. Beyond it, we can only speculate, guided by mathematics, symmetry, and the unflinching logic of physical law. So when you hear about the edge of the universe, remember, it's not a place where existence ends. It's the horizon of our knowledge, forever shifting, forever outpaced by the expansion of space. The true universe, whatever its extent or shape, remains shrouded in mystery. And the edge is only the limit of what we can observe, not the limit of all that is.
What would it actually mean to travel to the edge of the universe?
Imagine climbing into the fastest spaceship possible, pointing it in one direction and never stopping. Would you eventually crash into a cosmic wall, like Truman at the end of his show, peeling back the illusion to reveal what's beyond? Or would you just keep going endlessly with no edge to find, only more and more of the same universe? Or could you somehow loop back to where you started, like an ant crawling around the surface of a globe? The reality, grounded in physics, is more radical than any science fiction concept. First, the idea of traveling to the edge assumes there is an edge in the conventional sense, a border, a wall, a place where space itself ends. But all our best theories say otherwise. In most modern cosmological models, there simply isn't a physical edge out there. Space is either infinite, extending without bound, or it's finite but unbounded, wrapping around in such a way that you can never leave or find a true frontier. If the universe is infinite, then traveling in any direction is just an endless journey. You'll never encounter a boundary because none exists. You'd simply pass more galaxies, more stars, more cosmic voids forever. The universe doesn't run out. If, on the other hand, the universe is finite but unbounded, like the surface of a higher dimensional sphere or torus, then, after traveling far enough in a straight line, you could, in principle, return to your starting point without ever finding an edge. This isn't just a philosophical game, it's a real mathematical possibility allowed by Einstein's theory of general relativity. But what does relativity itself say? Special relativity places an ultimate speed limit, the speed of light. No matter how powerful your spaceship, you can never break this cosmic speed law. Even at light speed, the distances are so immense that reaching the edge of the observable universe, let alone the whole universe, is effectively impossible. Meanwhile, general relativity tells us that the geometry of space can be curved, looped, or stretched in complex ways, but nowhere does it require a sharp edge or ending. In fact, relativity allows for even stranger scenarios. The expansion of the universe means that distant regions are receding from us faster than light, not because they're moving through space, but because space itself is stretching. This creates cosmic horizons. Beyond a certain distance, the space between you and that region grows faster than any signal or object could ever cross. Even if you could travel forever, you'd never reach those unreachable zones. They're simply beyond your causal reach. You're trapped within an ever-shrinking bubble of what's accessible, not by any wall, but by the relentless dynamics of space-time itself. And if you somehow could keep accelerating, chasing the edge, relativity produces another mind-bending effect. The closer you get to the speed of light, the more time slows down for you relative to the rest of the universe. In the extreme, you'd experience time dilation so intense that the universe outside would seem to rush forward. Galaxies aging, stars dying, cosmic structures evolving in the blink of an eye. Yet, you'd still never reach a boundary. All you'd find is more and more space receding ever faster. What about a finite universe with exotic topology? If the cosmos is wrapped around like a three-dimensional torus or sphere, then, in principle, traveling far enough in a straight line would bring you back to where you started, without ever encountering an edge. The universe would be like a giant cosmic video game, where the map loops in all directions. You could see your own back, given perfect vision and enough time for the light to make the journey. But you'd never find an end. You'd be caught in an eternal loop, traversing the same space forever. Could there ever be a true boundary? In all known physics, the answer is no. Any hypothetical edge would break the very laws that govern space and time. If such an edge existed, the equations of relativity and quantum field theory would no longer apply at that boundary, and reality would become unpredictable, perhaps even nonsensical. No evidence for such a breakdown has ever been observed. All measurements from the structure of the cosmic microwave background to the most distant galaxies show smooth, continuous space with no signs of termination. Even the concept of an edge in higher dimensional models, like brane worlds and string theory, doesn't give you a conventional wall. The edge is really a transition to another dimension or a change in the laws of physics, not a place you can reach by conventional travel. So what would it mean to travel to the edge? In every serious scientific model, it means nothing at all. You'd never find an edge, a wall, or a curtain. You'd encounter either infinite space or a universe that wraps around itself. The structure of space-time, governed by relativity, quantum mechanics, and the observed expansion, prevents any hope of ever discovering a boundary. The universe doesn't just hide its edge, it eliminates the very concept. Travel as far as you like. Space will always provide more. There's no end, no edge, no final destination. The only limits are the laws of physics, the speed of light, and the unstoppable expansion of the cosmos. Humanity's visions of the universe and its edge have always been more than just scientific questions. For thousands of years, every culture has stared up at the night sky and asked, "What's out there? Is there a limit? Could we ever reach the end?" The answers have ranged from the practical to the mythological, the wildly imaginative to the eerily prescient. And these worldviews still echo in the way we approach cosmic boundaries today. In ancient Mesopotamia, the universe was often imagined as a flat disk, bounded by a dome, the firmament, separating the earth from the heavens above and the underworld below. The Greeks gave us the concept of a cosmos, a harmonious, ordered whole, sometimes infinite, sometimes walled by crystal spheres that carried the planets and stars. Perhaps the most famous ancient image is the world turtle, the cosmic reptile that carries the earth on its back. In Chinese and Native American traditions, the world floats on the shell of a giant turtle or rests on the backs of elephants, themselves standing atop further turtles, stacking down to infinity. This wasn't just a story, it was a way to grapple with the fearsome idea of endlessness, to give structure to the unknown. The edge in these systems was both literal and metaphysical, a place where order gives way to chaos, where known reality dissolves into primordial waters or endless night. Yet some ancient thinkers pushed even further. The Greek philosopher Anaximander speculated that the universe might be aperon, limitless, boundless, infinite. Later, Aristotle rejected this, insisting on a finite universe with perfect, nested spheres and a hard outer edge. But centuries later, in medieval Europe, new models emerged. Chinese cosmology envisioned the universe as round like an egg, with a layered structure, heavens above, earth below, and beyond the great void. The idea of an edge was woven with philosophy, the boundary between yin and yang, between the material and the spiritual. In Mesoamerican cultures, the universe was often pictured as a multi-layered world, with boundaries not just at the physical edge, but at each level of reality, a vertical as well as horizontal stratification, marked by thresholds, gates, and guardians. Indigenous Australian Dreamtime stories describe a world emerging from chaos, with boundaries not just in space, but in sacred meaning. The edge is less about geography and more about the limits of human experience, knowledge, or spiritual power. These visions were more than just fanciful. They shaped how early scientists and philosophers cackled infinity. The fear of the infinite haunted European thinkers well into the Renaissance. Infinity was seen as the domain of God alone, dangerous for mortal minds to contemplate. When Copernicus, Galileo, and Kepler shattered the medieval crystal spheres, the idea of an infinite universe, a cosmos with no center and no edge, became both liberating and deeply unsettling. Modern science still carries traces of these ancient fears and dreams. The edge of the universe, in contemporary cosmology, isn't a wall or a shell or a final curtain. It's an observational limit, a mathematical construct, a conceptual boundary that's always moving as our understanding grows. Yet we still speak of horizons, frontiers, and the limits of knowledge, language inherited from millennia of cultural grappling with the unknown. Even today, philosophical debates continue. Some see the universe as a single, closed system, an unbroken totality with no outside, echoing Aristotle's finite cosmos. Others, inspired by quantum mechanics and the multiverse, imagine endless realities, a modern twist on the world turtle with universe upon universe, no ultimate edge in sight. So do these cultural and philosophical traditions offer us anything for today's science? Absolutely. They remind us that the concept of a cosmic edge isn't just a technical question. It's a deep challenge to the human mind, a place where science, imagination, and myth intersect. Our models and equations may be new, but our fascination with boundaries and with what lies beyond them is as ancient as humanity itself. And in a very real way, these stories shape the questions scientists ask. They push us to explore beyond the visible, to rethink what we mean by infinity, to wonder if the true edge is not a place in space, but a limit of perception, understanding, or imagination. The journey to the cosmic boundary is as much about confronting the limits of knowledge as it is about mapping the universe itself. Physics is a relentless engine for overturning our deepest intuitions. With every new advance, from Newton to Einstein to the quantum revolution, the universe has revealed itself to be far more alien, mathematical, and unforgiving than anything imagined in legend or tradition. So what happens if we push the frontiers further into realms where our current understanding collapses? Could the next breakthroughs in physics completely rewrite what we mean by infinite, edgeless, or boundary? Are these merely provisional concepts, destined to be shattered by the next leap in theory? Start with quantum gravity, the holy grail of modern theoretical physics. Our two most successful theories, quantum mechanics and general relativity, work flawlessly in their own domains, but break down when you try to combine them at the Planck scale, where distances shrink to 10 to the minus 35 meters and energies explode. At this scale, the very fabric of space and time isn't smooth, but wildly turbulent, a quantum foam seething with fluctuations. Here, the concept of continuous infinite space may not survive. Space itself might be quantized, with the smallest possible unit, a pixel of reality beyond which the notion of distance is meaningless. If that's true, infinity as we know it is fundamentally redefined. There are no infinite lines, only a vast but finite lattice of space-time quanta. The edgelessness of space could be an illusion, replaced by a granular, discrete structure. String theory offers an even more radical shift. In this framework, the fundamental constituents of reality are not particles, but tiny vibrating strings, existing in as many as 10 or 11 dimensions. Most of these dimensions are compactified, curled up so tightly that they're invisible at human or even atomic scales. In string theory, the universe could have multiple topologies, boundaries in higher dimensions, or even branes, higher dimensional surfaces on which our universe exists. The edge of our universe might be a transition to another brane, another sector of the cosmic superstructure. What we think of as infinite could just be a local patch, repeated or mirrored in the vast landscape of string theory vacua. Then there's the holographic principle, an idea born from black hole thermodynamics and quantum gravity. It suggests that the information contained in a region of space can be described entirely by what's encoded on its boundary. In this picture, what appears to be a three-dimensional, infinite universe is actually a projection from a two-dimensional surface, a kind of cosmic hologram. The edge in this scenario is mathematical, not physical, and infinity becomes a question of information density, not spatial extent. Loop quantum gravity, another approach, posits that space is woven from finite loops, quantized chunks of geometry. In this theory, the traditional notion of infinity fades. Instead of endless space, you get a network of interlinked nodes, a finite but unbounded structure. Boundaries, if they exist, are emergent properties, not sharp divides, but transitions in the underlying graph of connections. What about cosmic inflation? This idea, now supported by evidence from the cosmic microwave background, suggests that the early universe underwent an exponential burst of growth, smoothing out space and making it appear flat and infinite. But in some models, this inflation never ends. It spawns endless bubble universes, each with its own properties, stretching the concept of edge to the breaking point. Is infinity just a mirage, created by an unending process with each observer trapped in their own ever-growing bubble. New physics could also rewrite our ideas about the fate of the universe. If dark energy, the mysterious force driving cosmic acceleration, changes over time, space could rip apart in a big rip, tearing all structure down to the quantum level. Or the universe could tunnel to a lower energy state, rewriting the laws of physics everywhere and creating a true edge, not in space, but in the stability of the vacuum itself. And then there are quantum computational approaches, which model the universe as a vast quantum computer. In these frameworks, infinity is replaced by computational complexity. Edges are limits on information processing, not spatial barriers. It's possible, even likely, that our current ideas of infinity and edgelessness are just shadows on the cave wall, artifacts of limited observation and outdated mathematics. Future discoveries could reveal new kinds of boundaries, not walls, but changes in dimensionality, transitions in physical law, or shifts in the fabric of space-time itself. What seems infinite might be revealed as a loop, a fold, or a simulation, limitless only within the confines of its own logic. The next era of physics may force us to abandon infinity as a naive extrapolation, and edge as a human projection onto a much more complex dynamic reality. The universe will not care about our intuitions. It will reveal, as always, a structure at once colder, more abstract, and more awe-inspiring than any story told by our ancestors. Will we ever know if the universe has an edge? This is the question that haunts the very foundation of cosmology, driving some of the most ambitious scientific efforts ever undertaken, and at the same time exposing the ultimate limitations of our knowledge. The observable universe is enormous, but it is only a minuscule patch compared to the possible scale of the cosmos. The laws of physics and the speed of light conspire to keep most of reality forever out of reach. So is it even possible, in principle, to discover a boundary, or to know with certainty whether the universe is infinite or finite but unbounded? First, let's be brutally clear. Every observation we can possibly make is confined within the observable universe, a sphere about 93 billion light-years across, defined not by any true edge, but by the distance light has traveled since the Big Bang. No matter how powerful our telescopes, no matter how clever our instruments, we cannot see beyond this cosmic horizon. The universe could extend for trillions of times this distance, or it could loop back on itself in ways that even our wildest mathematics can barely describe. If there's an edge, it could lie so far away that its light will never reach us, not in a trillion years, not ever. But this isn't just a practical problem, it's a fundamental one. Every experiment, every measurement, every test of theory is filtered through the finite speed of light and the relentless expansion of space. Even if space is finite and wraps around like a torus or a hypersphere, the circumference could be vastly larger than the observable universe. We could be ants on a globe so large we can never hope to see its curvature, let alone return to our starting point. No signal, no particle, no probe could ever travel far enough to bring back information from beyond our horizon. Does this mean we're doomed to ignorance? Not entirely. Science is the art of inference, of building models, making predictions, and comparing them to the data we can collect. If the universe were small enough, or had a certain kind of repeating topology, we might observe patterns in the cosmic microwave background, or see strange alignments, statistical oddities. So far, none have been found, and the data is consistent with both an infinite universe and with a finite universe, so vast its boundaries are forever hidden. And what if the universe is infinite? Even then, we can never prove it with certainty. All we can ever say is that, as far as we can see, space continues without edge or limit. But the absence of evidence is not evidence of absence. The next horizon is always just out of reach. This ultimate uncertainty shapes the way we approach the cosmos. It forces humility into our science, reminding us that every conclusion is provisional, every theory limited by the reach of light and the laws of nature. The edge of the universe, if it exists, may be as much a boundary of knowledge as it is a physical reality. Yet it's precisely this uncertainty that drives exploration. The unknown pulls us forward, compelling us to build ever larger telescopes, to launch ever more ambitious missions, to peer deeper into the night. Every time we push back the horizon, we find new mysteries, galaxies at the dawn of time, the afterglow of the Big Bang, hints of physics that don't fit our models. Each new discovery reminds us that the cosmos is vaster and stranger than we imagined. But we are also confronted by limits we cannot cross. The cosmic event horizon, set by the acceleration of the universe's expansion, means that most of what exists will remain forever out of contact. Regions now visible will eventually slip away, their light redshifted beyond detectability, their information lost to us forever. Our cosmic island is shrinking, not in size, but in access. Could there be clues, subtle fingerprints of a boundary or topology buried in the data? Perhaps. The next generation of cosmological surveys, mapping the cosmic microwave background in greater detail, charting the distribution of galaxies on scales never before attempted, may reveal new anomalies, hints of structure, or signs of a more complex topology. Or they may simply confirm that the observable universe is a tiny typical patch of an infinite sea. In the end, the question of the universe's edge is a confrontation with the deepest limits of observation and theory. Science will continue to attack the problem from every angle: mathematics, experiment, observation, simulation, always seeking the next clue, the next pattern, the next way to infer the structure of reality from the faint signals that reach us. But some mysteries may always remain just beyond our horizon, tantalizing, unreachable, fueling our curiosity and propelling our search for answers into the infinite unknown. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.